This is Bill Farmer again. Welcome back to Software Engineering 2FA3, Discrete Math and Applications 2. Today we're going to be talking about nondeterministic finite automata. So last time we talked about deterministic finite automata. Nondeterministic finite automata are tuples like deterministic finite automata. They're similar. We have Q, capital sigma, capital delta, capital S, and capital F. And Q is a finite set of elements called states. Capital sigma is a finite input alphabet, and capital delta takes a state and a symbol and returns a set of states. So this is different than a deterministic finite automata, which just returns, I should say, a set returns a set of states instead of a single state. And then capital S is a set of start states, and capital F is a set of final states. And so the major difference, as I just said, is right here. It's capital delta is going to possibly return, will return a set of states. Now this set of states could be a single state, it could be an empty set, it could be a set containing multiple sets. And now we can define a function, capital delta hat, which takes a set of states and a string and returns a set of states. And the way it works is if you apply this to a set of states with the empty string, you just get back that set of states. If you've already processed applying this to a set of states A and a string X, and now you're going to apply it to the another symbol A, you basically take all the states that you have obtained for X, and then you apply delta to each of those states with A, and then you take the union of all of those. So these things, these NFAs, they were introduced in the late 50s by Michael Rabin and Dana Scott, who were both students of Alonzo Church. Okay, so let's look at an example. Here's a transition diagram for an NFA, and it accepts the language where the fifth symbol from the right is a 1. And so basically the way it works is you start off in Q0, you accept, or you can read as many zeros and ones. Then at some point you can decide you're going to read a 1, and then after that you can read one more symbol, then another symbol, then another symbol, and finally a fourth symbol. And at that point you will be in Q5 and you accept. So the idea is read a bunch of symbols, then read a 1, which will be the fifth from the last symbol. Okay, so this is an example of a NFA. I have a simple question about it. Which of the states in this NFA are different than states in a DFA? Okay, so I'm going to give you a moment to think about this. If you want, you can turn off your video, and when you're ready, come back. Okay, welcome back. So, which of these states are different from states in a DFA? Well, the answer is both Q0 and Q5. Q0 is different because it has two transitions for 1. A transition from Q0 to Q1 and a transition from Q0 back to Q0, both with 1. This is not allowed for DFAs. For DFA, you have exactly one transition for each symbol in your input alphabet. Now Q5 is different because notice it has no transitions at all out of it. And as I just said, for a DFA, you have exactly one transition out of every state for every symbol. Okay, so this is the correct answer. C. Okay, so here's the transition table for this NFA. And notice that here we have the 6 states, and these are the members of our input alphabet. And for each state and each input symbol, we have a set of states. And most of these set of states are singletons, in other words, a set of exactly one member, but the ones in red are different. For Q5, the outputs are the empty set. Remember, up here we had no transitions coming out. And for the case when we're in Q0 and we're reading the 1, we have 2 possible states. Now, a string is accepted by N, or NFA, if the set of states we can get to by reading X includes final states. So you can think of an NFA when it's processing a string. There's multiple ways it can read it because it has choices of which transitions to take. And if any of those lead to a state, when you're all done reading the string, if you're in a state that's a final state, then it's accepted. So could be multiple ways of reading it, but only one of these ways of reading it needs to lead to a final state to be accepted. Otherwise, the string is rejected, and we say the set or language accepted by an NFA is written as ln. So that's going to be the set of all strings accepted by N. And we say that a DFA and an NFA are equivalent if they accept the same language. Now, it's pretty easy to show that if we have a DFA M that accepts the language L, then we can construct an NFA N that accepts the same language. So the way we do this is we use the same set of states, same input, alphabet, same set of final states. The set of start states for an NFA will be the set of S, the start state for our DFA. And the only thing left to figure out is the transition function, capital delta. And so what capital delta would do if it's in state Q and we're reading an A, we will return the set, which will be a singleton, the set of the state that delta, our transition function for the DFA M, returns. So DFAs are easily simulated by NFAs. Now, if we have an NFA accepts a language L, then there is a DFA that also accepts L. And the proof is to use what's called the subset construction to produce the DFA. So we have this particular construction that given any NFA will produce a DFA that is equivalent. And we will look at this construction in just a moment. So basically, based on Theorem 1, we can say DFAs and NFAs accept the same class of languages, and this is the class of regular languages. Remember, we said the class of all languages accepted by a DFAs are called regular languages. Okay, so here's another question for you. Which of the following statements is false? And I'll give you a moment to think about that. Well, welcome back. Let's go through these statements. The first says a DFA must process an entire string to reject it. Yes, that's true. When you're processing a DFA, you process the entire string. You're always able to move forward from one state to another because there's always a transition for every symbol. So this is true. An NFA must process an entire string to reject it. No, this is not necessary. If you process an entire string and if you're processing a string and you end up in a state where there's no way to go, that string gets rejected. So this is false. You don't need to process an entire string and reject it. The empty string is rejected by a DFA or NFA, and without epsilon transitions, which we will talk about in a moment, if and only if the start state is not the final state. This is true. If here's the start state, and this is the first state we go to, the only way we can accept the empty string is if this is the state we start in. If the state we start in is the final state. So this is true. D is every string is rejected by a DFA or NFA if all the final states are inaccessible. So this is obviously true. The only way we can accept a string is by getting to a final state. If all the final states are inaccessible, that means when we start in the start state, there is no way to get to those final states. Then every string will be rejected. Okay, here's another question. The question is, what can we say about a DFA and an NFA that are equivalent? So imagine we have a DFA and NFA equivalent. What can we say about them? What would be true? So I'll give you a moment to think about that. Okay, well let's look at the possible statements and see which ones you thought were true. If they're equivalent, by definition, they accept the same language. So this is true. They have roughly the same number of states. This is false. DFAs usually have more states than NFAs, and sometimes many more states than NFAs. NFAs allow us to write. An NFA allows us to write a finite automaton that's much more compact than we could if we were writing such one with the DFA. The ease of construction is about the same for both of them. No, this is false too. NFAs, as you're going to see, are much easier to construct than DFAs, generally. The ease of verifying that a string is accepted is about the same for both of them. DFAs have a very simple way of accepting a string. You basically just process the string one symbol at a time, going from one state to another. With NFAs, we go from sets of states to sets of states. So it's a more complicated process to verify if a string is accepted. So this is false. Okay, so now we're ready to look at the subset construction. I'll remind you the idea of this construction, or the purpose of this construction, is we have an NFA, and we want to construct from that NFA a DFA that is equivalent. This is the subset construction. So let's say here's our NFAN, and we're going to construct a DFA that's equivalent. Well, the idea is that our DFA will use as states, it will use sets of states of n. So n is a set of state, Q n is a set of states. We're going to look at the subsets of this, and those subsets will be the states of n. And we may not need all these states, but generally speaking, if n has n states, our m will have 2 to the n states. So it could have many more states than n has. And here's how the construction works. So I just said that the set of states of M will be all the subsets of Qn. So that's pretty easy. And our transition function will take a set of states and a symbol, and it will basically return the set of states that we can get to, starting with the states in A and reading A. So we'll return all those states that we can get to when we have a set. We're starting with a member of A, and we're reading member of capital A and we're reading little a. Okay, so that's how the transition table works. Our start state will be the set of all start states of n up here. This actually should be capital N. And the final states will be all the subsets of the states in Q. So all the states in QM that contain final states of N. And then it's pretty easy to prove that our delta hat is going to be the same as, I should say, little delta hat will be the same as big delta hat. So little delta goes for our machine M, and big delta goes for our machine N. And there's a theorem, which is fairly easy to prove, that M and M are going to be equivalent. So let me give you an example. So here we have sigma. It has this input alphabet, and the language that we want to accept is a set of all strings over sigma, where the second symbol from the right in the string is a 1. So here is our NFA. So basically, we start in state Q0. We can read as many zeros and ones as we want, but when we're ready to complete our string, reading the last two symbols, we read a 1, go to Q1, and then after that we read a 0 or 1, and then we are in the accept state. So this is very clear that this NFA is going to accept that language. So here is the transition table for this NFA. Notice if we're in Q0 and we're reading a 0, we stay in Q0. If we're reading a 1, we can go to Q0 or Q1. If we're in Q1, we go to Q2, reading a 0. And if we're in Q1 and we're reading a 1, we also go to Q0. If we're in Q2, we can't go anywhere. So we basically go to the empty sets. So here's the transition table for the DNF we're going to construct using this subset construction. It's going to have as states all the subsets of these states. So we have the empty state, the singleton of Q0, singleton of Q1, Q2, and the pair of Q0, Q1, the pair of Q0, Q2, the pair of Q1, Q3, and the triple Q0, Q1, and Q2. So we have all these states. Here we have 3 possible states, and here we have 2 to the 3 possible states, 8 of them. And the transition table is pretty easy to build from this table. So basically, where can we get, if we have the empty set of states, where can we get from those? Obviously, we can't get anywhere, so we have the empty set here and here. If we have Q0, where does Q0 go? Well, we look at this. Q0, when we're reading a 0, goes to Q0. When we're reading a 1, it goes to here. So we have the same things for here and here. Same way with Q1. These are going to be the same. And Q2. Now, if we have Q0 and Q1, basically, where can we get from Q0 or Q1 when we're reading 0? Well, it's going to be the union of these two. That's what this is. And the union of these two, which is this one. And so forth, we can fill out the rest of the table. Well, for instance, if we look at this set of the triple, and we're reading a 0, it's going to be the union of all of these sets. And for a 1 will be the union of all these sets. Okay, so this is a transition table, and the start state will be the set of the start states of this, which is this. And the final states will be all the subsets of Q0, Q1, and Q2 that contain Q2. So it's going to be this one and these. So these are the final states. And that's it. We've constructed the DFA. Now, notice that some of the states are written in green, and these states are in green because they're inaccessible. There's no way, if you think about it, if we take the first one, Q1, and look over here, there's no way we can ever get to that state, a state consisting of the set just Q1. There's no way we can get to that, so that's not accessible. Same way with Q2. Q2 does appear here and here, but we can't get the Q1, so we can't get the Q2. And then there's the state Q1, Q2. You will see Q1, Q2 doesn't appear anywhere here. And there's no way we can get to the empty state because the only empty state only appears here, and in order to get to here, we have to get to the empty state, and there's no way to get to the empty state. So these states are not accessible, and we could just drop those out of our DFA. We don't have to include them because they're not accessible. Okay, so this is the transition table, and if we write, using that table, construct a transition diagram, we get this deterministic finite automata. And notice it seems a lot more complicated. So this DFA seems a lot more complicated than this NFA. In fact, this NFA is very straightforward. It's easy to understand what it's accepting. It takes more observation to figure out what this is accepting. And so this is a clear illustration that NFAs are easy to construct. They're compact, but they have a more complicated way of processing a string. DFAs tend to be harder to construct. They're bigger, they're more complex in the sense they have more states and more transitions, but they're easier to use to process a string. Okay, well, we have one more topic, and this topic is about epsilon transitions. So far, we have DFAs and we have NFAs. And now we're going to have another kind of finite automaton, which is going to be called NFAs with epsilon transitions. So an NFA with epsilon transitions is an NFA where we're also allowed to have transitions of this form, where we go from a state P to Q by epsilon. And what that means is if we're reading a symbol P in state P, we can immediately go to state Q without reading any symbols. So if we're reading an A here, we immediately go to Q with an epsilon transition, and we will still be reading an A. So we make a transition without processing another symbol. And these epsilon transitions are very convenient. They allow us to design our finite automata much easier than if we didn't have these transitions. And they're especially useful, which we'll see later, for building NFAs out of smaller NFAs. So if we have NFAs that are going to be components of a bigger NFA, and we're going to put these together to build the bigger NFAs, epsilon transitions are very useful for this. And it turns out that if N is a NFA with epsilon transitions, then there's an NFA M prime without epsilon transitions, such that it accepts the same language as N. Epsilon transitions do not allow us to accept more strings or accept more languages. Here's a sketch of the proof. So let N be an NFA, and then we're going to define N prime. I should say let N be an NFA with epsilon transitions, and we're going to define N prime as follows. It will have the same state, same input alphabet. It's going to have the same final states, but we're going to change the start states and we're going to change the transition function. And we're going to use this using something called the epsilon closure. So if we have a state and we have an epsilon transition to another state, something like this, and we're at this state, let's call it Q, the closure of Q will be all the states we can get to by using epsilon transitions. So it looks like here the epsilon closure includes these three states as well as Q. So a transition function will just be the normal transition function, but then we imply the closure to it. So we do the normal transition function, we get to a bunch of states, and then we add to it all the states we can get to using epsilon transitions. And then S will be all the states we can get from the start states by epsilon transitions. Okay, so that completes our discussion today about non-deterministic finite automata. And so we'll stop here, and next time we're going to continue with another topic, an important topic, regular expressions. Goodbye.